Picture this. You're standing before a stone pyramid deep in the Guatemalan jungle, and you suddenly realize that every step, every angle, every opening in this millennia-old structure has been calculated to capture with millimeter precision the exact moment Venus will appear on the horizon 300 years from now. How could a civilization that supposedly didn't know the wheel or possess metal instruments predict solar eclipses more accurately than 16th-century European astronomers? This is one of history's greatest puzzles. A mystery that challenges our understanding of what advanced scientific knowledge really means. For centuries, historians and archaeologists have underestimated the intellectual sophistication of pre-Columbian peoples, but recent discoveries reveal a reality that forces us to completely rethink our view of science and mathematics in human history. If you've come this far driven by curiosity to unravel this fascinating mystery, consider subscribing to support us on this journey of discoveries that challenge what we thought we knew about the past. Today, we're diving into one of humanity's most extraordinary intellectual achievements. To truly understand the magnitude of what the Maya accomplished in astronomy, we need to transport ourselves to the dense rainforests of Mesoamerica between 250 and 900 CE, a period archaeologists call the Classic Era, when this extraordinary civilization reached its intellectual and scientific peak. During this time, while Europe was plunged into the Dark Ages and much classical knowledge disappeared from monasteries and libraries, across the ocean flourished a society that had developed a mathematical system more sophisticated than Rome's, created calendars more accurate than the Julian calendar, and established astronomical observatories whose precision would only be surpassed by modern telescopes. The Maya weren't a primitive people living in simple harmony with nature, as they're often romantically portrayed. Instead, they were a complex urban civilization with cities housing tens of thousands of inhabitants, sophisticated intensive agriculture systems, trade networks spanning thousands of miles, and, most impressively, a scientific tradition that combined rigorous empirical observation with mathematical calculations of mind-boggling precision. Their cities weren't just administrative and religious centers, but true open-air astronomical laboratories, where every temple, every plaza, every architectural structure had been carefully oriented to serve as an instrument for observing and measuring celestial movements. What makes this story even more fascinating is that the Maya developed all this knowledge completely independently of old-world scientific traditions, creating original systems of mathematical notation, unique methods of astronomical observation, and cosmological theories that, in many ways, proved more accurate than European concepts of the same era. They were the first people in history to conceptualize and mathematically use zero. Centuries before this revolutionary idea reached Europe through Arab scholars, and they developed a base 20 positional system that allowed them to perform astronomical calculations of extraordinary complexity. To understand how the Maya achieved such astronomical precision, we need to delve into the heart of their worldview and discover that, for them, astronomy was never an abstract science separate from everyday life. Rather, it was the very foundation upon which all human existence was structured, from the most important political decisions to the most intimate family rituals. Imagine a world where every birth, marriage, planting, war, and royal coronation depended on consulting the precise movements of the stars, where kings and priests ruled not only through military power or ancestral tradition, but fundamentally through absolute mastery of time's secrets and celestial cycles. This wasn't a society that occasionally consulted the heavens for guidance. This was an entire civilization whose social, political, economic, and religious structure had been meticulously organized around the most sophisticated astronomical knowledge the world had witnessed up to that time. In the city of Copan, in what is now Honduras, stood one of the most impressive achievements of Maya astronomical engineering in the 8th century. A complex of temples and observatories that functioned as a gigantic celestial calculating machine. Here, mathematician priests performed observations spanning entire generations, accumulating data with patience and dedication that challenges our modern mentality obsessed with immediate results. These structures weren't simple religious buildings, but scientific instruments of extraordinary precision, built with geometric tolerances so exact that every angle, alignment, and proportion had been calculated to capture specific astronomical phenomena with a margin of error that often didn't exceed a few minutes of arc precision that European astronomers wouldn't achieve until centuries later with advanced optical instruments. The most celebrated ruler of the city, known to archaeologists as 18 Rabbit, wasn't just a king in the traditional political sense, but rather a supreme astronomer-mathematician whose legitimacy to rule derived directly from his ability to interpret and predict celestial body movements with accuracy his subjects considered divine. This extraordinary king, whose royal hieroglyphic name was Waxaclahan Yuba Kawil, ruled Copan between 695 and 738 CE and transformed his city into a true open-air astronomical university, where Mesoamerica's greatest sages gathered to share knowledge, perform complex calculations, and develop theories about the cosmos's nature that would influence the entire region for centuries. Under his visionary leadership, monuments were erected that functioned simultaneously as symbols of political power, centers of religious worship, and precision scientific instruments. A synthesis of functions that reveals how deeply astronomical knowledge permeated every aspect of Maya civilization. The temples built during 18 Rabbit's reign contained staircases with exactly the number of steps needed to mark the days of sacred calendars, plazas whose dimensions reproduced mathematical proportions found in planetary cycles, and stones steelily engraved with astronomical dates and calculations whose precision would only be understood by modern archaeologists equipped with computers and celestial simulation programs. One of these stelae, known as Stela A, contains a date corresponding to December 9, 736 CE, but what makes this inscription truly extraordinary is that it doesn't only record a historical event, it includes retroactive calculations extending millions of years into the past, demonstrating that Maya mathematicians not only mastered observable astronomical cycles during a human lifetime, but had developed theories about the universe's temporal structure spanning geological and cosmological time scales. But the genius of 18 Rabbit and his contemporaries wasn't limited to passive observation of the heavens. They developed an integrated knowledge system that combined advanced mathematics, architectural engineering, scientific agriculture, and state administration in an intellectual synthesis of sophistication rarely equaled in human history. Their temples weren't just places of worship, but precise scientific instruments, built so their windows, doors, and alignments captured specific astronomical moments with accuracy that allowed them not only to observe eclipses and planetary conjunctions, but to predict these events decades or even centuries in advance, a capacity that gave them immense political and religious power over the populations they governed. The mathematical system that made these extraordinary calculations possible was based on a revolutionary conceptual innovation: the invention and systematic use of zero as a real number, not just as empty space or absence of quantity. While Romans struggled with their additive numbering system that made complex calculations impossible, and Europeans would take centuries to adopt zero brought by Arabs from India, Maya mathematicians were already routinely using this fundamental concept to perform operations involving astronomical numbers. Literally, as many of their calculations dealt with time periods spanning millions or even billions of days. The rival city of Palenque, in present-day Chiapas, Mexico, became famous for an even more impressive innovation. Its architect astronomers developed a system of astronomical windows in the royal palace that functioned as a three-dimensional perpetual calendar, where sunlight penetrated through specific openings at precise celestial moments, creating light and shadow patterns that revealed complex information about the cycles of Venus, Mars, Jupiter, and the Moon. This ingenious system allowed priest astronomers to carry out continuous observations without moving instruments, as the building itself functioned as a gigantic fixed astronomical instrument, calibrated to capture and record celestial movements with accuracy that impresses even modern astronomers. King Pacal, whose tomb in the Temple of the Inscriptions contains one of the most sophisticated series of astronomical calculations ever discovered, ruled Palenque for nearly 70 years and transformed it into a center of scientific excellence where some of the most advanced theories about time's cyclical nature and the universe's mathematical structure were developed. The hieroglyphs engraved on his sarcophagus aren't merely funerary decorations, but constitute a veritable astronomical treatise that includes calculations on Venus cycles extending more than 1,000 years into the future, demonstrating that Palenque mathematicians had developed formulas capable of predicting planetary motions with accuracy that wouldn't be equaled in Europe until the development of modern mathematical astronomy. What's most impressive about the records left by these wise rulers is the obsessive precision with which they documented not only the astronomical events they observed, but also the methods they used to make their predictions, creating a tradition of rigorously empirical scientific knowledge passed down through generations via specialized schools where young nobles spent decades learning not only to observe the heavens, but to think mathematically about the cosmos in ways that allowed them to anticipate its movements with precision their societies considered supernatural. These schools functioned as true astronomical universities, where not only observation and calculation techniques were developed, but also philosophical theories about the nature of time, space, and causality that would profoundly influence the entire Mesoamerican worldview. At Chichen Itza, in northern Yucatan, Maya architects built what is perhaps the most famous demonstration of their astronomical mastery: the Pyramid of Kukulkan, also known as El Castillo, whose geometry was calculated with such precision that during the March and September equinoxes, sunlight creates a perfect optical illusion, making it appear as if a serpent of light and shadow slowly descends the pyramid stairs, a phenomenon that attracts thousands of modern tourists but which, for the Maya, represented the visible manifestation of their mathematical theories about time's cyclical structure and the cosmos's geometric nature. This extraordinary pyramid isn't only an impressive monument, but a gigantic three-dimensional calendar, where each architectural element was calculated to represent specific aspects of the temporal cycles that governed Maya life. But the deepest secrets of Maya astronomy only began to be truly understood when archaeologists discovered and succeeded in deciphering the astronomical codices that survived the systematic destruction promoted by Spanish conquistadors. Extraordinary documents that revealed the existence of a scientific knowledge system whose sophistication defied all expectations about pre-Columbian civilization's intellectual capacities. The most impressive of these manuscripts, known as the Dresden Codex, contains astronomical tables that represent the pinnacle of Maya science, including predictions of solar and lunar eclipses extending hundreds of years into the future, calculations of Venus cycles performed with precision differing only minutes from values determined by modern astronomy, and mathematical formulas to correct small irregularities in planetary motions that European astronomers would only discover centuries later. This extraordinary codex, which miraculously survived the autos de fe ordered by Bishop Diego de Landa in 1562, when thousands of Maya manuscripts were burned in an attempt to completely eradicate indigenous culture, contains a section devoted exclusively to eclipses that demonstrates truly astonishing astronomical understanding. Maya mathematicians not only knew how to predict when eclipses would occur, but had developed methods to calculate their duration, intensity, and geographic visibility with accuracy that allowed them to determine whether an eclipse would be visible from specific cities. Crucial information for their religious rituals and political decisions, since they believed eclipses represented moments of particular cosmic vulnerability requiring special ceremonies to restore universal balance. The most revolutionary discovery contained in the Dresden Codex, however, was the revelation that Maya astronomers had identified and mathematically calculated what modern scientists call the eclipse recurrence period, a complex cycle of approximately 18 years and 11 days that governs eclipse pattern repetition. This cycle, known to ancient Greeks as Saros, was considered by Europeans one of classical astronomy's most sophisticated discoveries, but the Maya not only knew about it independently, they had developed refinements and corrections that made their predictions even more accurate than tables used by medieval European astronomers. Even more impressive is that the Maya were able to determine that the Saros cycle isn't perfectly regular, but exhibits small variations that accumulate over very long periods, requiring sophisticated mathematical corrections to maintain prediction accuracy. To solve this problem, they developed what we might call ecliptic supercycles, periods of hundreds or thousands of years during which eclipse patterns repeat with near-perfect precision, a discovery requiring centuries of careful observation and mathematical calculations of extraordinary complexity. Maya mastery over planetary motions reached its apex in the Dresden Codex's Venus tables, which reveal understanding of Venus's behavior so sophisticated that it included corrections for small irregularities in its orbital motion caused by gravitational perturbations from other planets. Venus was, for the Maya, much more than a simple object of astronomical observation. It represented a fundamental deity in their cosmology, associated with both war and love, and its cycles of appearance and disappearance determined propitious moments for battles, marriages, coronations, and cosmic renewal rituals. Maya priest astronomers discovered that Venus has extremely complex behavior when observed from Earth, alternating between periods as morning star and evening star with durations that vary slightly from cycle to cycle, creating patterns that repeat completely only after periods of decades. To master these intricate cycles, they develop a calculation system that combined rigorous empirical observation with advanced mathematical modeling, using formulas that could predict not only when Venus would appear or disappear, but also its exact position in the sky, its relative brightness, and even subtle variations in its apparent color caused by changes in Earth's atmospheric composition. The accuracy of these Venus calculations is so impressive they differ from modern values by less than 2 hours in predictions spanning decades, a margin of error considered exceptional even by contemporary astronomy standards. This extraordinary precision was only possible because Maya astronomers kept continuous observational records for hundreds of years, amassing an empirical database so extensive and reliable it allowed them to identify and correct even the most subtle irregularities in planetary motions. But perhaps the most impressive achievement of Maya astronomy was developing their integrated calendars, a temporal system of unparalleled complexity and precision in human history, which combined multiple astronomical cycles into a unified mathematical framework capable of situating any event in time with absolute accuracy. This system didn't consist of just a single calendar, but a series of interconnected calendars functioning simultaneously, each based on different astronomical phenomena. The 365-day Hab based on a solar year, the 260-day Tsokin derived from complex ritual and astronomical cycles, and the long count that allowed dating events on a timescale spanning millions of years. The genius of this multiple calendar system lay in its ability to synchronize astronomical cycles that don't have simple mathematical relationships to each other. a task requiring not only precise observations but also developing sophisticated mathematical theories about the nature of irrational numbers and decimal approximations. The Maya discovered, for example, that the true tropical year isn't exactly 365 days long, but approximately 365.2422 days, and developed methods to incorporate this complex fraction into their calculations so their calendars remain synchronized with seasons for periods of thousands of years. This discovery of the tropical year's actual length is particularly impressive because the Maya made it without optical instruments, relying solely on careful visual observations made over centuries. They identified that if they used a calendar year of exactly 365 days, their calendars would gradually misalign with seasons, with the spring equinox occurring progressively earlier each year. To correct this calendrical drift, they developed an extremely sophisticated intercalation system that added extra days at mathematically calculated intervals to maintain perfect synchrony between their calendars and actual astronomical cycles. The most impressive Maya calendar, however, was the long count, an absolute dating system that allowed any event to be placed on a timescale stretching from a mythical date of the current world's creation to billions of years in the future. This calendar functioned as a gigantic temporal odometer, recording time's passage in hierarchical units including days, 20-day periods, 360-day years, 20-year periods, and so on, until reaching temporal units so vast they surpassed any practical necessity, demonstrating that the Maya had developed a truly cosmic conception of time that transcended individual human experience limitations. The mathematics underlying the long count reveals understanding of numbers and arithmetic operations rivaling old world civilizations' achievements, including mastery of concepts such as exponentiation, geometric progressions, and calculating large numbers requiring extremely sophisticated mathematical manipulations. Maya scribes could perform calculations involving millions or billions of units as easily as they manipulated small quantities, using algorithms that would only be rediscovered by European mathematicians during the Renaissance. But the most fascinating aspect of Maya calendars was their integration with direct astronomical observations, creating a hybrid system that combined theoretical mathematical calculations with empirical corrections based on continuous observation of celestial motions. Priest astronomers kept detailed records of small discrepancies between their calendrical predictions and actually observed astronomical events, using this information to constantly refine their calculations and develop increasingly precise corrections. This rigorous scientific approach, which combined mathematical theory with systematic empirical verification, represents one of the earliest manifestations in human history of what we would recognize today as the modern scientific method, demonstrating that the Maya had developed not only extraordinarily sophisticated observation and calculation techniques, but also a scientific epistemology that valued accuracy, verifiability, and continual knowledge refinement based on observational experimentation. When we contemplate the magnitude of Maya astronomical achievements, we're forced to confront an uncomfortable truth about our own intellectual prejudices and limitations. For centuries, Western civilization built its cultural identity around the belief that scientific progress followed a linear trajectory, inevitably culminating in European modernity's technological and intellectual superiority. The discovery that an American civilization had developed astronomical and mathematical knowledge that in many ways surpassed old world achievements not only challenges the simplistic narrative, but forces us to fundamentally rethink our understanding of human intelligence's nature and the diversity of paths by which different cultures can achieve scientific excellence. The Maya teach us that intellectual sophistication doesn't necessarily depend on technological complexity, but can flourish through the combination of careful observation, rigorous mathematical reasoning, and a cultural disposition to value accuracy and empirical verifiability. They were able to make extraordinary astronomical discoveries using only their eyes, their intelligence, and a civilizational patience that allowed scientific projects to span generations, demonstrating that true scientific progress lies not in the instruments we use, but in the quality of thought we apply to understanding the natural world. Even more profoundly, the Maya intellectual heritage confronts us with a fundamental question about our own time. In a world where we possess space telescopes capable of observing distant galaxies and computers that can simulate millions of celestial bodies' motion, have we developed the same reverence for precision, the same dedication to careful observation, and the same humility before cosmic complexity that characterized the sages of Köppen, Palenque, and Chichen Itza? The honest answer to this question may reveal that, despite all our technological advances, we still have much to learn from a civilization that managed to unlock the cosmos' secrets using only the sheer force of human intellect applied with extraordinary discipline and perseverance. Maya astronomical accuracy ultimately represents a profoundly human achievement that transcends cultural and temporal divisions, reminding us that the ability to understand and predict celestial movements is one of the highest expressions of our nature as a thinking species. When we gaze at the stars today, we carry with us not only modern science's legacy, but also the heritage of those ancient sages who, in Mesoamerica's jungles, dedicated their lives to the sublime task of deciphering time and space's secret languages, leaving us an eternal example that true human greatness lies in our infinite capacity to turn curiosity into knowledge and knowledge into wisdom.